Over the past year, I have built up this battery bank behind me. We have a tower of power, which is a bunch of lithium iron phosphate batteries. We also have this Chevy Bolt battery, and hiding over here in the corner, we have an LG server battery. Now all of this is parallel together and it's working really well. But what is the total capacity usable? Well, that's what we're going to find out today. Hi, I'm David. Welcome to my channel where I like to DIY renewable energy and energy efficiency projects. Today, we're going to wire up a water heater as a load. Now this will serve two functions for us. We're going to do a capacity test, but not just what 100% to minimum is. We're going to find out what the usable capacity is as it sits. The second purpose will be to wire it up to a relay that will be controlled based on state of charge. So when the batteries get full, it will divert the excess power to that load. Now this particular battery here, this is a Chevy Bolt battery, and this tested at 6 kilowatt hours on the bench. This one over here in the corner that's kind of hiding, well, that one tested at 2 kilowatt hours. This tower of power tested at 24 kilowatt hours. So we should have 32 kilowatt hours total. However, we're not charging it up to 100% or discharging it to 0% state of charge on every cycle. Now, part of that is because I want to extend the life of the battery, and if you kind of stay away from the top end and the bottom end in your cycling, you'll get more cycles total. But there's another reason that I don't charge it to 100% and discharge it to 0%. And that is, these are different chemistries. This is a lithium iron phosphate battery bank. This is a Li-NMC battery bank. Different chemistries will have different charging profiles. This battery has a different maximum voltage than this battery. As well, they have different minimum voltages. So what is the actual usable amount of capacity that I have available? I don't know. That's why we're going to run the test. This is my water heater in the corner of the garage. Now this tank style water heater holds 40 gallons of water and has two heating elements. Each heating element is a 240 volt AC element and it uses 4,500 watts. Now this is connected to the radiant floor system and solar system. The radiant floor system is this one right here connected with this thermostat, and it circulates through the radiant floor. There are 4 loops that go down to the floor, and then 4 that come back up here and back into the bottom of the tank, where it's then reheated if need be. The solar system goes through a heat exchanger and is separate. Now the total system works fine, but I'm going to change some of the wiring. I'm going to leave the top heating element wired to the grid exactly the way it is now. Now the grid being the garage and house grid, which really runs off-grid using these inverters that are SMA Sunny Island inverters most of the time, but not in the winter. I just don't have enough solar right now. I hope to change that in the future, by the way. This is where the power comes in from the grid and goes down to the top thermostat and heating element. We're going to leave this one alone exactly as it is. But if this one is satisfied and the thermostat is happy, it then sends the power to the lower thermostat. That's what we're going to disconnect. We're going to run a new wire just for this bottom thermostat and heating element. First thing we have to do is turn off the circuit breaker to this. Then we're going to take this cover off and disconnect the wires that go down. We're running 240 volts, and both the upper element and lower element are both 4,500 watts. But see how its total watts is 4,500? Both are only on one at a time. So right here is where we're going to turn off power. This top circuit breaker is the water heater, and it's off right now. It's on a 30 amp circuit breaker, which means it's going to be using 10 gauge wire, and that's also what I saw over there. So first we'll take off the top heating element cover. So this is some insulation, and everything's better with insulation, so I'm glad they packed this area. Now underneath we can see a plastic cover hiding the thermostat, and that right there is the water heating element. This is a water heating element, And what we are seeing is just those back two screws. With a multimeter, let's verify we don't have any power out here. Even though we know the circuit breaker's off, we always want to verify we don't have any voltage at this point. Now let's take off the plastic cover and check at the thermostat leads. So there's a red and black wire right at the very, very top, and that is going to be our two hot legs. So we're going to check right there. And no voltage. So we successfully turned off the circuit breaker, so there's no power out here. Now keep in mind, all of this wiring is exactly straight from the factory. I have never touched this. The power comes in at the top of the water heater, travels down on these two wires, so we have L1 and L2. These are two hot legs. This is a thermal overload switch, and it can be reset. Then the power goes to the thermostat, which is this one right here, and you can dial it in to whatever temperature you want. If this top heating element says that it's satisfied, it does not send the power to this thermostat. Instead, it redirects the power down. Right back there is a black wire, and that black wire is coming off this screw. But we also have a red wire right here, also coming off this leg. So when the power comes in here, this side is always going to have that. So we have a red wire that travels down, and this blue wire which goes to this thermostat. So those ones are always connected, and it goes down here. What is switched though is this black wire right there, or this yellow wire. The yellow wire goes to the top heating element. The black wire goes down to the lower heating element. These are the screws that are being switched. Either this one is on or this one is on, and it's jumping between them. So what I'm going to do is disconnect the red wire over here from this screw, and I can disconnect the black wire from this screw. That way we don't have the possibility of sending power down to the lower heating element. Because this upper thermostat has the additional protection, I went out and purchased the exact same model number upper thermostat, but I'm going to install this one down here and switch it out for the bottom thermostat. That way we get that extra protection even on the bottom circuit. Now I have heat shrink on the ends of the two wires, so there's the black and red that lead up. They go up there next to the tank, and then they pop out up here. We have the black one and the red one. Now that these wires are insulated at each end, we don't have to worry about them shorting out. Now I'm going to remove that thermostat and put in the new one. These thermostats are held in with two little clips, one on each side, one here, one here. So all we really have to do is pull those clips back and push up. In fact, let me try to just push this out of the way. This is the old thermostat, and here's the new one. So if we flip this over, this is the snap disc thermostat. So when the metal expands, it will snap open, and when it cools off, the metal will snap shut. And same here, except this one has two. So that's the thermal overload switch, and this one is the regular thermostat. So the thermostat just automatically goes in and out. This one needs to manually be reset. So it's exactly the same as up top. We'll just install this, and it should install the same way. So let's see. It's there's no glue or anything that gets put on these. At my local home improvement center, I picked up some parts for this project. Well, here's the wire that I picked up for the project. Now the water heater needs to be run with 10 gauge wire. That's what this 10 is for, and that's because it's on a 30 amp circuit breaker. 2 means 2 current carrying conductors inside here, plus a green insulated ground. So there's actually 3 wires inside, but one of them is a ground. Now metal clad, that's why we call this MC. And it says black and white. You can also get this, say, 10-3, and then you'd also have a black, white, and usually a red in here as well. So this is 90 degrees C, THHN, THWN. So it's all good, UL listed, made in America. Now these are the little clips that I'll be using to clip this in place. This is a 90-degree fitting that I'll use to run this into the water heater, and a straight fitting that can go into the box. Now these are little plastic bushings. You'll see a little bit later, but this bushing will go around the wires and protect them from the metal cladding from shorting out. So we're going to break this out. We're going to get it in place. So I'll get it installed with these clips, And I'll just use some 3/4 inch long screws. These are screws that I use for a lot of these little projects. So the metal clad cable is a little bit better than, say, Romex, which is a non-metallic sheathed cable. For this type of application, I'm going to be running it overhead in the garage, and it's not going to be protected inside a wall. Now, if I make any mistakes at all, I do apologize. I'm not an electrician. I'm just a DIYer. So please let me know in the comments below if I make any mistakes, and I'll be sure to fix them. Also to note that codes will vary anywhere you go, from state to state, country to country, and even town to town, which is one of the most aggravating things about where I live. So I drilled a hole in the outside metal, as well as the plastic shroud on the inside. So now we can get those wires through that. To cut the cable, I made a mark on the metal sheath, which is aluminum, that lines up with the hole. And there's a service loop here, so if you need to play with it, you have some slack from that point. So now we'll just cut this off. They do make a really cool tool that just kind of clamps on this, and then you turn it almost like a can opener, and it will cut a little notch in there. I don't have that tool, so I'm just going to use a little rotary cutoff tool like a Dremel, but this one happens to be from Harbor Freight. And we're just going to come in here where those two marks are and just very lightly notch the outside of the metal, but don't go too far because you don't want to score the wires inside. So now we should be able to crack that off. Yep. See, I just untwisted it, and I didn't even break the plastic that's inside of that. So now this will come off if I just give it a yank. Now we need to protect this. We don't want the wires to break on that sharp metal edge. So let me go get one of the bushings. So this is one of the little red bushings that's going to protect the wire. So we'll put this on the outside. This will just feed over the wire, like that. And then we slide it in. So the bushing is all the way around. Now we'll undo this plastic around the outside. Fold that down over it. This is the 90-degree fitting. So we'll just open this up, feed the wires in. There we go. All right, we're done wiring. We have the wires coming in through that hole, and they go to the top two screws, then they come down to the lower thermostat. So I added that white wire, so it should be good. Under here, I have a Victron Smart Shunt. It is the 500 amp version. That Smart Shunt connects with Bluetooth to my phone. I can see how many amps are moving in and out, and it's very accurate for measuring the total watt hours moving in and out, or amp hours. Now today was a sunny day, and I allowed the whole battery bank to charge fully. It's at 100% state of charge. We sat in absorption mode until the absorption amps dropped down to 1 amp. So they are certainly at full voltage. I use a Victron charge controller on one of my solar arrays. That charge controller is set to 56.8 volts. That is the maximum voltage for the whole pack. Now if I wanted to, I could zero out the smart shunt and do the capacity test just with my normal loads in the garage and in the house. But if I did that, the loads would vary. And then when I go to do another capacity test at some point in the future, when I add more things, those loads will change. So instead, I would rather have a fixed load, being a water heater, very consistent, to do the capacity test, drain the whole battery bank down. Now I will stop it at 48 volts, and that's the cutoff that I have set in the BMS. I want a consistent load so that as I add batteries in the future, or I change things up, or change the inverters, or whatever I decide to do, if I want to do another capacity test at some point, I can turn on the exact same water heater, have the exact same load, and compare the two with those controls in place. I don't want all these variables. I just went into the app for the Victron Smart Shunt and I reset the history. So now it is all zeroed out, and I just turned on the inverters. They're going through a little diagnostic right now, and I turned off the solar coming in. So now what will happen is, as soon as this starts, we'll be able to start the discharge test. We're currently 100% completely full. There's all the cells. And this battery pack is attached, and I even threw this one on. It does have a circuit breaker, but obviously that's not a good way to do it. That's going to be going into the server rack, but both of these batteries are attached to this through the bus bars, so we'll be able to measure all of the discharge. Now, grand total, this is all 32 kilowatt hours, but we don't charge it 100%, and we're not going to discharge it 100%. We're going to stop at 48 volts. Okay, looks like we can start it. Press and hold. And so now, I'll just turn on the water heater. Right there. You could actually hear them kick up. 4.3 kilowatts. And this water heater is kicking on, this one right here. I just checked the shunt, and it says 4,600 watts is being discharged through the shunt, and this says 4.3 kilowatts. That tells me that these two inverters are using 300 watts right now in the conversion process of taking the DC and making the AC. The test finished up showing 27.7 kilowatt hours. It finished last night, well, technically this morning. We were after midnight, and I went to bed after that. Now I stopped the test and took that screenshot at the exact moment that we went from 48.00 volts to 47.99 volts. I wanted to get this capacity test done because I'm about to add some more batteries, and I wanted to see what they were just as is. Now after this, I'll have to set up the relay in the SMA inverters so that the electric heating element in the water heater can turn on automatically whenever the battery pack reaches a certain level. So stay tuned for future videos on that project. Thank you everybody so much for watching. If you enjoy the videos, please like, subscribe, comment, and share.